All right, we'll just give it a minute or two and let everybody trickle in.
Sounds great.
All right, welcome everybody to this webinar hosted by the research committee called Building Towards Inclusivity in Building Performance Simulation. Our presenter today is going to be Dr. Tarek Sherif. Um, Dr. Sherif holds a PhD from the Georgia Tech School of Architecture, where his research explored the use of technology and simulation tools to improve building performance with an emphasis on inclusivity and representation of disadvantaged communities in BPS. He also earned a MS in computational data sorry, analytics and an MS in architectural technology from Georgia Tech. His expertise lies in applying automation and simulation to streamline evaluations, enhance energy efficiency, and ensure equitable benefits across diverse communities and building types. As head of building science and operations at Lamar.ai, Tariq is currently leading efforts to scale advanced building envelope inspections by making them more accessible, cost-effective, and accurate. Thank you so much for joining us today, Dr. Sherif, and I will turn the time over to you.
Well, thank you so much for the introduction and for the invitation. Let me share my screen. All right. Again, thank you everyone for the invitation. Today I'm going to be talking about the pursuit of inclusivity in building performance simulation. I'll start off just by giving a quick background about myself. I got my formal education first in architectural engineering back at the American University in Cairo. Then I first started by coupling that with a building science perspective, which I got doing MS at the Georgia Institute of Technology. Then I thought to myself, no, I need to also combine this with more education in data science analytics perspective. So I got an MS in analytics at Georgia Tech before finally all of this culminating in my dissertation or PhD work that I did at Georgia Institute of Technology. Now I'm currently working at Lamar AI, where we're working at automating building envelope inspections with the goal of making these envelope inspections more accessible. So part of it is, of course, making it more accessible or easily to implement for things like disadvantaged communities that we'll start or touch upon today. But what are we going to be talking about today? So what are we going to be exploring? We're going to first start off by defining the problem. Why do disadvantaged communities or neighborhoods need new approaches to building simulation? Then we'll talk about pathways for refining simulation inputs for those communities on the axes of climate, building systems, and people. We're going to be talking about how we can integrate different workflows and develop future directions for how we represent disadvantaged communities in simulation models. And finally, we're going to be concluding with key lessons and where we go from here. So why do disadvantaged neighborhoods need a new approach to building simulation? While there's been significant work on improving energy efficiency in the built environment, specifically for households and residential structures, disadvantaged communities are currently in a worse situation. Energy consumption was proportionately 3 times higher than their affluent counterpart in those disadvantaged communities. Individuals were more likely to live in older, energy inefficient buildings. They're more likely to be energy insecure. and electricity consumption was attributed specifically, or elevated electricity consumption was attributed to the design and construction of the households in which these disadvantaged communities live. And while weatherization becomes a tool for us to improve the energy efficiency of those communities, there's an issue that we face when we apply wide-scale adoption of those retrofit strategies in the absence of on-site data. As we have seen in the literature, that such a homogeneous adoption of strategies can have diminishing and even in some instances detrimental effects on building condition. And this is where usually simulation comes in. So simulation, and throughout this webinar, I'm going to be discussing more the applications for physics-based simulation models. Have a lot of applications in terms of analysis of energy consumption, optimization of system design, cost and life cycle assessment, again, and the last part, retrofit and renovation planning. And if we look at the typical process that we do is we have a building data, we start off with a building data set. And from that building data set, we have a distribution of buildings with their specific characteristics. Now, in typical simulations, what we do is we start off by having that data set, we link it, or we start to build or construct prototypical templates. This could be for BEM or UBEM models. And these templates sort of encompass a lot of information that we have about the building. So it can encompass things like the wall assembly, the windows, the flooring, HVAC systems, lighting equipment, etc. And then we use that prototypical template into our simulation model, or feed into our simulation model. But if we're looking at what the issue is with the disadvantaged communities, is that while these prototypical templates are constructed based on the majority of the distribution, the issue with disadvantaged communities is that they lie at they are the outliers of those distributions, meaning that the archetypes or templates that we do produce do not capture the characteristics of those homes quite accurately. And the conditions we can see, or the results of this, is that we can see up to a 92 kilowatt hour per meter square per year difference in EOI between simulated and actual energy consumption in some instances. So what this highlights is there's a need for us to consider or carefully inspect the model fidelity in such instances. And model fidelity here represents the degree to which the model or simulation reproduces the state and behavior of the real world object. So if we're looking at the objective that or a clear objective that we need currently, specifically for disadvantaged communities, is for us to enhance the representational fidelity and predictive accuracy of physics-based building and urban energy simulation models, and specifically make sure that it is applicable for or across diverse morphological and socioeconomic contexts, with a particular focus on disadvantaged communities. And because we have been talking, or in the field of architecture now, we've reached a state where we have understood, or we have clear understanding of the boundaries of what it means to have inclusivity on architecture. And what this next step allows us to do is to move from inclusivity in architecture towards more inclusivity in building performance simulation. And what do we mean? And for this specific webinar, what we mean by inclusivity in building performance simulation, it involves the integration of diverse perspective, needs, and conditions within the modeling of building systems and energy performance. And the key objective of it is that we want to ensure that the benefits that we're seeing from things like simulation, from all of the tools that we're getting, even advances in weatherization, that it becomes more equitably distributed to marginalized and underserved communities. So in terms of research questions that we all need to consider, first off, what are the key obstacles and challenges hindering the calibrated integration of disadvantaged community into physics-based and urban energy simulation models? Secondly, if we're looking throughout the simulation process, if we're looking at first the setup where we're generating the inputs, where we're doing the simulation specifications, and then we're providing the outputs for a specific simulation run, we need to critically analyze and inspect the type of inputs that we're generating for the prototypical templates that we're producing for these disadvantaged communities. So second questions could be, how can the simulation and fidelity be enhanced to produce more representational outputs for BEM and UBEM simulations? And how can the formulation workflow be streamlined so that it becomes more adaptable to a wide, and of course also adaptable to a wide variety of socioeconomic factors and conditions, meaning that we can apply the current workflows, that the streamlined workflows in a lot more contexts. And if we're looking specifically, one key thing that we have been missing right now in building performance simulation is the representation of the influence of socioeconomic factors on physics-based simulation models. So currently, there's a lot of instances in practice where we use a singular representation of occupant and behavior. But of course, a multifaceted occupant characterization is often required, specifically for disadvantaged community. So here there arises the question of how energy poverty and vulnerability could influence occupant behavior in disadvantaged communities. And then what methodologies do we need to develop for us to represent such behaviors in the future? And then finally, if we're talking about always equitably distributing the advancements in technological in terms of benefits for everyone, how can we use the forefront of what is being worked on, namely digital twins? So how can we integrate current energy models for disadvantaged community to work towards digital twinning? So we move from a snapshot model to more of a real-time updated model. So the last thing would be, how can digital twinning approaches be developed to represent like the unique energy and environmental challenges faced by disadvantaged communities? So starting off, how can climate, building systems, and people better be represented in simulation models? So first, to understand how they can be better represented, we need to talk about what are the current limitations. So what are the current limitations of physics-based simulation models? Again, we talked about a large difference between simulated EOI and actual energy consumption, meaning there's a large disparity in simulation results. There's a failure we talked about if we're applying the insights gained from energy simulation models into retrofit. We talked about the failure sometimes to improve energy consumption or thermal comfort, meaning that there's an ineffectiveness for retrofits that are backed by simulation inputs, and which can also lead, in some instances, we see into compromised indoor air quality if and mold growth. So even with, in some instances, we can see detrimental retrofit results. And again, this all lies to what we talked about before, that outlier conditions for disadvantaged communities make their representation building performance simulation much more trickier than usual. So if we're talking about what are the key things that influence in terms of those outlier conditions, it would be first, we have external environmental forces. So we can see temperature, for example, temperature differences in the microclimate that we need to capture, elevated occupant density in certain instances, proximity to mobile and stationary sources. So these things like that can, of course, affect as well pollutant concentrations, amongst others. So all of this are external factors that we need to incorporate into the simulation models in terms of being an outlier. When we're talking about building systems and appliances, for example, when we can see things like deteriorated building construction assemblies, HVAC system inefficiencies. So like we can see it very, very old-fashioned split units that are very, very bad in terms of efficiency, for examples. We can see building envelope. We can see that we need to adjust the building envelope. We can see issues with electric appliance performance that we need to address. All of these things that could be, for example, captured through if we're talking about, of course, building construction assemblies, and the state of the envelope could be captured through thermal imaging to support that. And finally, and of course, at the core of what we need to do is how do we represent occupancy patterns and space use? How do we incorporate things like socioeconomic factors into first the occupant limitations and behaviors as a reflection of those limitations? So all of the three axes that we talked about, namely weather, external climatic condition, building systems, and appliances, and then people, all of these sort of highlight the need to localize simulation input specifically for disadvantaged communities, just because what we talked about before, that they lie more at the outlier conditions, so they're not easily represented through prototypical templates that we have. So how can we start to approach that localization? We can start to approach it through, for example, leveraging existing data repositories. As we know, of course, now with the Internet of Things, we're gaining exponential, or we're having an exponential growth in household data sets describing both conditions, energy consumptions, and of course, weather conditions, amongst others. So we need to leverage these existing repositories to feed into our simulation models. In instances where we don't have existing data, and this, by the way, happens a lot for disadvantaged communities, because the majority of the data we have for more affluent communities. In the instances where we don't have those existing data repositories, how can we start to leverage things like specifically data capturing technologies? So there's a lot of technological advancements over the past decade. So how can we start to capture existing conditions as is, rather than relying on prototypical templates in this case? And finally, how do we incorporate socioeconomic inputs in building simulation models? So how do we represent socioeconomic factors into building simulations? So if we start off by creating some, again, examples at the climate, building and systems, and people scale, when we start off with climate, for example, what would be an issue or a challenge that we could see when we're trying to represent climates in building performance simulations? One thing was that we see is that, let's say, if we're doing a prototypical simulation, we start with either a TMY, typical meteorological year, an AMY, actual meteorological year, or an extreme meteorological year that have been used previously. And we sort of feed that into NG Plus simulation software. But the challenges that we do have is that for these three factors that we just highlighted, is that they often lack the spatial proximity to where we're trying to conduct the simulation. And you might think that might not be an issue, but looking, for example, at an image here, which again is on a larger scale, but looking at it, and an example for Los Angeles, for example, we see that there's a large difference or a large difference in temperature as a result of tree canopy coverage. And what we saw is specifically, for example, for this specific instance, is that there is a large difference in outdoor temperature condition, the largest amongst all 50 states, between affluent and non-affluent communities. So to just use either TMY data or AMY data captured from a weather station that is far removed from where the community lives can misrepresent the actual temperature conditions at that particular location. So we see residents having, for example, to start using more applied ways of managing that sort of microclimate conditions and try to reduce their feeling of extreme heat, for example, in these instances. So how do we start to develop ways of capturing the microclimate in building performance simulation? This becomes a key challenge that we need to sort of start thinking about and start making it more streamlined. And in this case, so one example that we did through our own research is that we start to think about the idea of localizing weather file creation for a select community. So what we aim to do is to have a file that sort of incorporate the influences of things like urban texture variables, account for things such as urban heat island effect, and most importantly for things that operate under data scarcity scenario, meaning that in the lack of data, we're able to impute information sort of to keep the simulation going. And what we advocated for is the production of an inclusive meteorological year weather file. And specifically, again, I'm going to talk briefly about the specific case study that we had, is we had it for Atlanta, Georgia. And what we wanted to do to showcase is for things like existing repositories, such as weather stations, in the Weather Underground repository that has over hundreds of thousands of weather stations across the US. We can start to leverage that to produce more tailored EPW files or inclusive meteorological year weather files for those disadvantaged communities. And what we show is that if doing that, we can get a better sense of the temperature profile in comparison for disadvantaged communities as a comparison to TMY or AMY, for example. Okay, moving from climate conditions, a second axis that is very important to consider is core buildings and systems. So there's a need, for example, to be able to accurately, and of course this is important for our simulation models, accurately represent the envelope conditions, for example. So how do we approach buildings where it's more difficult to estimate the envelope conditions on site? And here, what we started to advocate for, or what we should consider, of course, are non-destructive techniques for extrapolating this data as a first layer. And we need to evaluate different ways in which we can capture that critical information for those communities. So how can we start to use, of course, things like blower door test analysis to get the air tightness. We can start to leverage things like infrared thermography with drones to capture anomalies in the building envelope and better characterize the performance of the envelope. We can even link with utility bills or data if we do have them to sort of calibrate the model. And even surveys and interviews, because sometimes discussing with the residents themselves, the residents, of course, know best how have a great understanding of how their space is operating. So even discussions with them in terms of surveys and interviews can provide great insights in those instances. And what we wanted to show through one instance is how can we, for example, is how can we use emerging technologies such as thermal imaging with drones to rapidly capture and sort of characterize existing building conditions for those communities. So what we did is through one research paper is that we looked at pre-retrofit analysis and post-retrofit analysis for both identifying where the areas that need to be sort of weatherized or where intervention is needed. And then post-retrofit, we were able to also analyze whether those interventions were successful or not. So this gives us a way where we can immediately give both feedback for the people doing the intervention and then post-intervention evaluate the effectiveness. So there's a need to leverage these sort of emerging technologies to accurately capture building characteristics. And finally, and of course, most importantly, people, how we represent people in building performance simulation, specifically for disadvantaged communities, is critically important. And again, we talked about before that currently in most instances in practice, there's a singular representation, but we need to move more towards a multifaceted occupant characterization if we want to have a better representation of occupants in those simulation models. And if you might ask yourself, let's say, what's the issue between not having an accurate representation of occupants or having one? And the issue is often that if we're looking at simulated consumption using a prototypical template and then actual energy consumption on site, we can see that socioeconomic factors for things like, for example, education, things like employment, and things like income can sort of significantly change and create a distinct difference between simulated consumption and actual energy consumption on site. So for us to move more towards a better representation of occupants, specifically in building performance, both BPS and UBEM, there is a need to sort of start off by looking at physics-based simulation model and then calibrating the deterministic simulation inputs. So for example, if we look at things like lighting loads, for example, if we know specifically exactly what type of lighting is being used in those residential homes, we can start to extrapolate those inputs. But we need to sort of calibrate also using social insights. We need to calibrate the occupant inputs that we use. So social insights can include things like, again, socioeconomic factors, first of all, or even the form of surveys that would help us sort of calibrate those simulation inputs with the goal of sort of a simulation model representation that best, or more accurately represents conditions on site. But for us to go on this endeavor, this of course has to be sort of supported by a layer of deep social engagement. And again, if we're talking about social insights, these type of deep social engagements need to take shape in the form of discussions and forums with the residents. There are more that could provide us both insights and help us also move the simulation work that we're doing into practicality through applying some of the things that we do suggest if they find it or deem it fit. So if we're talking about, for example, simulations and how to represent occupants in simulations, usually the prototypical thing, for example, and an issue we see in building performance simulations at the moment is we start off with an occupancy schedule that sort of prototypically feeds into the HVAC control systems and in our case feeds into the simulation model. But we fail sometimes to incorporate how things like restrictions or limitations on incomes can significantly affect the operation of HVAC systems, even with in retrospect, of course, the occupancy schedules that we have. So, for example, if we look at prepayment plans, a lot of households that are in disadvantaged communities are enrolled in prepayment plans, which means that homogeneous adoption of HVAC system throughout the year is not applicable for them because they have, of course, income limitations. So the question then becomes, how do we incorporate such socioeconomic factors to better also represent actual behavior of simulations in those conditions? So as an example of a research project that we worked on, we looked at a neighborhood in Atlanta, Georgia, and we looked at that in which the majority of residents, over 70% of residents, had enrolled in a prepayment plan. And we looked at what the simulated energy profile looked throughout the year against what their prepayment plan limit was in respect to households in good and in poor conditions. And just as a reflection, what we saw, for example, if we're looking here, these represent here the prepayment plan limits. As a reflection, we saw that the simulated energy consumption, assuming, of course, continuous operation of HVAC systems throughout the year, uh, uh, often lay above what the prepayment plan limit was, meaning that the simulation assumes that the HVAC operation is going to be continuous, but in reality, those households face discontinuities in service or opted to completely alter their own behavior in their households in order to stay under that prepayment limit plan. Meaning in instances where we just apply it homogeneously, we are not able to capture what the actual energy behavior are for those households. And if we're looking at instances, for example, where we're even modeling things like thermal comfort, if we're again if we're then assuming a continuous operation of HVAC system throughout the year, we see that of course households between different conditions would have a similar condition of indoor air temperatures indoor. But once, if we consider things like financial limitations, we see that households, let's say, for example, in poor conditions, reach that financial limitation much quicker. And accordingly, if we talk about HVAC system or discontinuing HVAC system operation for a majority of the month or a portion of the month even, it means that it has drastic implications on thermal comfort implications for those households. So here, this is more of an example of how incorporating one socioeconomic factor, such as financial limitations, could significant or should influence how we see those simulations or interpret the results of those simulations. So what does it look like for us to sort of integrate socioeconomic context and then looking into the future? How can we move towards things like digital twins, for example? So what we sort of advocate and what the title of this webinar is the idea of trying to work towards an inclusive both BEM and urban energy building energy models. And these need to be grounded in localization of simulation inputs for us to gain better fidelity in terms of the simulation outputs, of course. So it needs to start off first, starting off by the unit. We need to start off by localizing and critically analyzing how we can get and formulate the archetypes for those communities, for example. So how can we get things like construction assemblies through technologies that we were discussing? How can we extrapolate lighting and equipment power densities, for example, through surveys that we can do with the residents or through any data capturing methods? How can we calibrate the occupancy and people representation that I was talking about before for us to incorporate things like socioeconomic influences and how those should be represented in those occupancy schedule at the unit scale? And then moving from the unit scale, we can start to look at the building scale, for example. How do we understand some sort of information or link that to information? And in this instances, of course, I'm talking about UBEM models. So how can we link an understanding and quickly generate what the building footprint is, what the height is, what the window to wall ratio is, and then how can we assign the different archetypes for the buildings in a neighborhood? So if we're looking at again, doing an urban building energy simulation model, and we're looking at the neighborhood of a house on 100 households, how can we assign the archetypes based on our understanding from available data sets on site and our understanding of how the actual conditions of those households are? And finally, how do we link that at the sort of city scale or a large neighborhood scale? How can we look at weather file localization so that we can escape the discrepancies between just using either a TMY from a weather station that is sort of removed from where the community lives, but rather use a localized weather file that's able to capture the subtleties that we can see in temperature based on local climate, local urban texture variants. So for example, we talked before about, let's say, vegetation. Let's say vegetation coverage, of course, would impact, let's say, when we talked about tree canopy and things like that, vegetation coverage definitely impacts the temperature conditions on site. So how do we incorporate that into our simulation models? And then finally, and this is, or not finally, but a next step would be we have all of these informations that we're generating for or localizing. Of course, they're going to be geometric, semantic, and consumption. But how do we link that to real or near real-time data for data analysis and scenario predictions, if we're going to be moving from a snapshot of building performance towards digital twins as we're moving towards now in the building performance simulation community. So how can we start to give insights real time, for example, to residents about how their current performance is, what their current building characteristics is, and accordingly, what the implications of doing certain interventions would be? Because the goal in the end, of course, is to try to improve the conditions for those households. So what would be the key findings or lessons that we wanted to discuss today? So one key lesson, again, we highlighted this before, is that we talked or we have been exposed a lot to inclusivity in architecture, but we need to now also start to consider inclusivity in building performance simulation. Namely, because we want the implications of the simulations that we're doing, the analysis that we're doing to have a beneficial impact for those communities. And we want an equitable distribution of those beneficial sort of interventions that we do across communities, across socioeconomic classes that we're sort of targeting in this case. And secondly, and we talked about the idea of input calibration, we need to think critically about pathways that we can sort of start calibrating the input specifically for disadvantaged communities. And we talked about how we can do that for things like climate building and systems and people using technological advancements, existing data repositories, or even questionnaires, and specifically interactions and the better representation of occupants in building performance simulation. But this is sort of a starting point where we can start to improve the fidelity of simulation models. And it's important to understand that improving the fidelity of simulation models, of course, would have a larger benefit for disadvantaged communities. But of course, improving the fidelity also holds benefits for all simulations that we produce on a regular basis. And the goal is this case is to bring this number down. And we highlighted this maybe at the beginning of the talk that we were going through, is the idea that there are currently 30% of disadvantaged households fail to pay at least one energy bill throughout the year, meaning that there's a lot of beneficiaries in which we need to do interventions to improve building conditions, to reduce their energy poverty, and to improve living standards for those communities. So we need to bring this number down for those communities. And the way to do that would be to apply conscious simulation models that are able to sort of incorporate localized inputs that are more representative of the actual conditions on site for those households. So we can apply weatherization based on those simulations and improve conditions in those households. And again, the idea of localizing or improving simulation fidelity has a ripple effect that it not only, of course, improves conditions specifically for disadvantaged communities, but it can also help with researchers, policymakers, affluent communities, industry software developers. This would be something that could improve the current fidelity of simulation models for a lot of stakeholders in our process. Yeah, that's what I wanted to discuss and wanted to hear your thoughts about it today, and would like to hear what you think and how you think we should advance building performance simulations to become more inclusive of disadvantaged communities. So I'd like to, just as a follow-up, open the floor. If anyone has any questions or anything they would like to discuss, please let me know. Like any questions of, let's say we do be like what are the issues you think exist in representing disadvantaged communities in building performance simulations? Or what are pathways you think for that? Or what are key challenges you saw working in those communities? Any type of question is, of course, extremely. I'd be very excited to talk extensively about. Yes, please go ahead. Go ahead, Graham. I saw, one second. Okay, I'm giving you the floor. Hi, Graham. Can you try talking now?
Oh, sure. Yeah. Yeah. Thanks. Um, thanks so much, Tarek. Fantastic stuff. And this isn't, I don't know where this is just a question that popped in my head. When you're talking about understanding different communities and their sort of indicators, their sort of behaviors, it seems like a huge task, different cultures, different kind of I don't know, just a lot of diversity within disadvantaged communities. Keep- just kind of curious about that. If you obviously, I'm sure you thought about that, but let you speak a little if you're willing.
Yeah. No, I agree with you completely. It is a huge endeavor. I personally think that yes, it is a huge endeavor, and in the majority of cases, we might not get the fidelity of the data that we do need or be able to represent the way that we do want. However, I think we should also not shy away from doing it. I think that the sweet spot or what we should strive for is to at least first start off by more like incorporating things like socioeconomic factors in building simulation models, where of course in physics-based simulation models, we know because we're focusing primarily on the physics-based sort of calculations, we often do not include these at all. So things like, again, income, education, things like that. And then starting from there, we can start to sort of build to the extent of the fidelity that we need for a certain application. But to echo your point, it is a huge, it is a huge task, and of course, this might be the reason that a lot of people like do not try to incorporate those factors into their own simulation models. However, given its influence on simulation results, I think it would be still warranted for us to definitely incorporate such things. One
Awesome. Thank
second.
you.
Yeah, I'll go through the questions as well. I saw, what do you see as applications for digital twins? Is it affordable? Do you see as applications for, I'll just read the question out loud for everyone to. So the question was, what do you see as the application for digital twins in low-income neighborhoods? And is it affordable for this? So this is a double question. The first part is a dual thing. So what the applications for digital twins would be in, and that's what the applications for digital twins would be in low income neighborhoods. One thing is, of course, to give the residents first feedback about the current state of their buildings, whether it is performing as at standard or not, where the issues are, because if we're talking about a digital twin, we want the digital twin to also be representing the building characteristics, for example, so we can immediately give them feedback about improving certain systems, improving, let's say, an HVAC system, window to wall, like window construction assembly, things like that. But in our own work as well with disadvantaged communities, one of the things that we see a lot is that some of those, let's say for neighborhoods, a lot of those neighborhoods, they lack the information required to request funding for things like weatherization. So a large application for such things could be is that given this, if we do develop this breadth of information, that we do provide this to the community, and then the community is able to take that sort of information and then head to, let's say, people who are providing incentives, like people who have funding for things like weatherization and things like that. So they can go to them and gain the necessary funding to weatherize or improve the condition of their own households. This was something that was repeatedly highlighted to us, is that for every community we worked with, they also always highlighted, great, we can now use this information to go to funding entities and obtain the required funding for that. In terms of how affordable it is, I think in practicality, previously, of course, it was not, but I think as technological advancements continue to happen, and as the sensors that we now require. So we are working with now sensors in a community where the sensor itself costs less than 50 to $60, I think, to produce or to source in this case. And the upkeep for having such a sensor installed is less than a cent a day. So if I think in the future, as these sensors become much, much more affordable and streamlined, I think capturing the necessary data, at least for electricity consumption, might be easily done. The other parts that we need to supplement the digital twin with, which is, of course, the information about the building systems, the information about the construction assemblies, this still requires us to think about how we can link that to energy consumption. But I hope this answers that first question. Okay. Second question that I saw is, I would like to hear your thoughts on how folks are able to get better data on hyper-local issues, urban heat islands, proximity to mobile and stationary pollutant sources which impact indoor air quality, and the design decisions on operable windows versus closed and filtered fresh air trade-offs, but then resiliency might make it better to have operable grazing. So in terms of getting this question, thank you for the great question. I think this question highlights that we need to have better data sets for hyperlocal issues, and I definitely agree with that. So I think it depends, of course, on the available resources, as it as it always does. But the first thing is, I would approach that, and we should approach it at least as a multi-layered like solution or way to address this issue. Is first, if we discussed or talked about this briefly, is having maybe non-destructive techniques, or maybe having sensors even installed can just quickly gain an understanding of what the issues are, or just get a sense of what, let's say, for example, what the temperature are and as a reflection of urban heat islands, or what the pollutant concentrations is. So sensors become a thing that we could use. A second thing, and I think for us is becoming much, much more accessible, is again data repositories. Like if there's emerging data repositories that have critical information. It's just that for us, or for a lot or a majority of practitioners, we don't know how to access it most efficiently. So a lot of times there might be a data set, at least for let's say a local one. I mean by that, local weather station that is pretty close. Like you can find maybe a weather station that 100 something like that meters to where you are, but you're not able to access that information just because you're not aware of it. So I think it's first is, of course, the application of data capturing technologies to feed into such things, or such decision making. But the second thing is we need to start to have a clear understanding of what the available sources are, and we're getting more and more sources, of course, by the day. I'll look at now there's a third question. It says, I'm helping design a movie theater which will be 100% accessible per ADA requirement. It really helps to have someone on the team with a disability helping with this effort. However, I found this particular individual is so nice, she tries to compromise more than she should. For example, she may say, I can adjust a steeper ramp than is normal if it is too hard to manage other design constraints. I have to remind her not to compromise 100%. Yeah, this is a more of an observation, of course, and I do agree. Like it's like because my research and the research that we've been doing over the past like 4 or 5 years, it entailed a lot of discussions with individuals from disadvantaged communities. So we saw a lot of community members that were more liable to sort of sacrifice in some instances their own comfort, unfortunately, for other reasons. So I definitely echo what you say there. I remember having a discussion with a couple who were in their 60s who did not like want or need or think it is important to have an HVAC system. Of course, this is up to their preference, but I agree that uh, individuals in those communities might be sometimes more liable to like endure discomfort more than, let's say, the standards are for thermal comfort in those situations. And in this case, the question then becomes, how do we have a simulation model that both recognizes those, let's say, those tendencies of the residents, but also into the simulation model, but also proposes ways that would help those individuals see the benefit of change, not changing their behaviors, but offering alternatives that they can apply. And yeah, I will definitely for Graham, I'll definitely share and my email address here in case anyone. Are there any questions or any things you wanted to discuss? Other things? Okay, yeah, I see in the Q&A, I just saw a question or two questions. What databases could be used with indoor temperature, energy consumption data? Uh, that's a really, really good question. Of course, to answer this question, this is going to be highly related to where unfortunately there's some data sources that are like apply to a large or the majority of the US. But I think to answer this question, we need to understand where we can find where the location is that you're trying to find this data for. So for this question, I'll just write up my email, and I think if you because for the person who posted this question might not be open to disclosing where it is. If you can send me a specific region of where this is, we can discuss further what type of available data sets are there. The second question from Anurada Kadam. Listening to this presentation and thinking about how disadvantaged communities are often not included in energy simulation because they're considered outliers makes me think about how we are only now starting to consider extreme weather events in energy modeling as well, because extreme weather events are now occurring with higher frequency. Similarly, more and more people are facing energy burden as prices are skyrocketing. Is there any way to take lessons learned from the emerging methodologies behind including extreme weather events in energy simulations and apply it to inclusion of disadvantaged community profiles in energy modeling? I think this question highlights a key thing that we have been observing is that right now we've gained more knowledge, or we're started now to incorporate things like extreme weather events in energy modeling more often. And with climate change, with changes in the climate, there are projections that talk about increases of extreme weather events by the double, that they're going to double in the future. So it's critical to incorporate extreme weather events. I think a really important thing to consider for these extreme weather events, specifically when it applies to disadvantaged communities, is the available infrastructure for those disadvantaged communities. So does that say first of all, we're talking about, let's say if we start by the neighborhood scale, uh, does the infrastructure for those neighborhoods account for a situation where there might be, or the grid, for a situation where there might be a higher or an extremely higher elevated demand than usual? Because in some instances, it comes that for those disadvantaged communities, the grid as well, or some of the infrastructure is not there to handle that information. And then the second layer would be, does the existing building conditions for the residents, is it able to also consider extreme weather conditions? So how can we talk about the performance, let's say, because we're talking about an outlier conditions in terms of the existing building systems and external climatic conditions, and occupant behavior and operation under limitations such as financial limitations. The question then becomes, if we couple that with extreme weather conditions, we can have instances where the situation that becomes extremely detrimental for the people living in those homes. And accordingly, yes, there is of course a need for further investigations on the topic to discuss extreme weather events in the instances of disadvantaged communities and how it impacts both the well-being and how we can create simulations to anticipate scenarios as such. Yeah. There's any other questions anything on anybody's mind to discuss? All right. Otherwise, thank you everyone for joining. It's of course this is a topic that's near and dear to my heart, so I can talk about it for hours. But I think generally speaking, to sort of conclude here, is that definitely for disadvantaged communities, we need to have better building performance simulation models, or specifically better workflows that produce and create those simulation models for us to get insights in which we can help communities and allow a more equitable distribution of the advancements of technologies for those communities, so we can improve both the building performance and alleviate the detrimental effects that those communities encounter. And thank you everyone for joining, and looking forward to talking to or interfacing with you all again in the future. If there's any questions, any follow-ups that you would like, my email would be tsherif at, I'll just type the email here in the chat. Please feel free to reach out and would be happy to discuss further. And thank you so much.